All right, guys, welcome back. Happy to see everybody again. We got 6 more weeks to go for the course, of course, plus the gap between the exam. But we'll talk about it once the exam schedule is released. Quick announcement. Of course, the most important thing will be for your programming test number 1 on Thursday. Nothing else to say. You know what to do. Just make sure show up in time to WSC, and then I'll be there greeting you. Your makeup lecture, which I spoke about, please, if you are interested, feel free to express your preference about whether you want a pre-recorded lecture or in-person lecture on Friday. I don't really have personal preference. I really enjoy in-person lecture, as you can see. But if you guys really prefer pre-recorded lecture, I'm okay with it. That's very good quality too, right? Just complete a survey. It's on the X and Z E-class site, and I'll make a decision very soon and let you guys know in time. Your assignment number 3 is due to release next week. And that one there is going to be about trees, which I will start today, about the trees. I'll make sure you're at least properly prepared before next Wednesday, or at least before next Thursday, the latest. You will be ready to enjoy the assignments. Assignment number 3 and assignment number 4 will be both on trees and some combination of trees, singly linked list, and recursion. We're going to put everything together in these 2 assignments. So you can really learn a lot from these 2 assignments. All right, and for your programming, oh, sorry, I don't really mean programming test 2. I do apologize. I really meant written test. Right? What I'm doing here. Okay, so anyway, I think I completely messed up with this comment here. What I really meant to say was for your written test, which is going to be in about 2 weeks' time, I will also release the guide for you. All right, sorry for the confusion. I'll reach out to you about the written test. And again, for this week, I only got 1 hour for you guys because I need to be also present for other sections and also coordinate things. I do apologize for that. But if you really want to speak to me for last minute question, you're still welcome to come tomorrow, 3 p.m. for 1 hour. Okay. All right, any questions about the course? All right, so now I would suggest forget about the stress for programming test 1. Let's now worry more about trees. I think that's important. Okay, for programming test 1, you can worry about it maybe after this class today. Okay, and just before that, as convention, let's now do a very quick recap about what we said the Thursday before the reading week on that snowstorm day. All right, let's now take a look. So basically, for that one there, we were introducing you about doubly linked list. And okay, very quickly. So we talk about just exercises about how you can insert after, insert before. So these operations could be useful, for you to implement as part of your algorithm for your programming test 1. So definitely worth going over them about the steps. And we talk about this comparison table. I'll do one more as a last bit to finish off the lecture about arrays and linked lists. But you can go over the details. It's also in the recording. You can check them out. And we talk about doubly linked list. So again, you can also review all the details, but the most important thing is about the summary right here. Okay? So why do we need to extend the singly linked list that we had into a doubly linked list context? One is for performance, and it's really for adding a previous reference so we can do certain operation more efficiently, asymptotically. Right? I'll review what the operation is very soon. Oh, actually, it's here. Remove last, basically, right? You can basically get a previous node in constant amount of time because it's an attribute access. And also, we talk about code structure, which we also spent quite a bit of time before the reading week. So we got header, we got trailer. You only need 2 helper methods, like an add between and also remove. Using these 2 helper methods, you can implement the rest of the methods in the doubly linked list. Right, just keep that in mind. And I also gave you guys some exercises before the reading week. Give a try. It's going to be very useful for your written test. I also gave the solution video as well on the lecture site. Check them out if you need to go over. All right, we talk about the Java implementation for doubly linked list, doubly linked node. We talk about these add between, and also we also talk about remove. Right, so these 2 are the important helper methods for you to really understand first before you look at the rest of the methods for doubly linked list. So I may not dive into details today, but I'll study them, and then once I resume the regular office hour next week, you're more than welcome to speak to me about the material. Right? You definitely need that for written test that's coming. All right. Alrighty. Any question about singly linked list, doubly linked list, or what we spoke about so far? Any part you want me to clarify? All right, sounds good. You can study that and let me know later. Take your time. All right, so I want to do just one more table right here. And so this table here is going to put all the linear data structure we have spoken about so far. Once we finish this table, we'll move on to non-linear data structure, which is more fun, actually. We'll see. So we got array, we got singly linked list, and we got doubly linked list. And one thing just to remind you, so for this part over here, we have already discussed them in detail in the previous table, right? So for this part here, I may not repeat. So this is, you can see the earlier discussion, okay? It's already there. And let's now take a look at what if we got doubly linked lists into play, right here. All right. So what we got is, for doubly linked lists, we still have the size. We still got the header that get next, and also trailer that get previous. We can easily get first and last element in constant time. So that's why there will still be big O of 1 right here. All right. And then for this one here, if you want to get some element at index I, if I is rather close to the middle, like n divided by 2, there's no way around. Either you go for the next reference from the left, or you go for the previous reference from the right. You will still get n over 2, which is asymptotically linear time, right? So for that one there, it will still get linear time, right? That's a very important insight. So previous is not like a silver bullet that can solve everything. What it does solve is this row here, all right? That's the most important row to really see. So you can see the remove last element right here, right? You can see for the remove last, for singly linked list, it is linear right here, right? On the other hand, for doubly linked list, it's going to be big O of 1, right? So that's really the difference you want to see. And for that one there, it's big O of 1. All right, that's important, okay? And then here we just talk about if you are somehow given the reference to remove or to add. So for doubly linked list, because it's like a natural extension to singly linked list. So what used to be big O of 1 for singly linked list, it will surely be a doubly linked list constant time as well, right? That should be no surprise. The final row would be when you are not given certain reference for add or remove, you still need to figure out exactly what the reference is. In that way, you will still get linear, okay? So everything here in the summary has somehow been discussed in certain parts of the lecture earlier. So please take a look and then really use this summary table here as a guidance for you to review all the aspects of these three linear data structure. All right, that's all I wanted to say about linear structure. Any question? All good? Go ahead.
So on the bottom right, I just
yeah.
saw you put the constant time. So that's
for
1D.
I definitely meant linear time. Thank you so much. I really appreciate that. Thank you so much. Absolutely. Linear time. Thank you. Yes. All right. Yeah.
Oh, why do you have like a shaded out pink box for removing the last element?
Sorry, say it again.
In the singly linked section,
yeah.
Why is there a shaded out pink box?
Oh, okay. So that one there, I just want to highlight the special operation right here. So you can see here, we talk about remove last, right? If you want to remove the last element in the singly linked list, all you got is the tail. But the tail is not enough for you to remove the last. You need to get a previous node, like a second last node. But you don't have such node. So all you got to do is you got to go all the way from the left to the second last node. That'll be linear time. But in the case of the doubly linked list, it's going to be constant because you got a trailer. You can say trailer that get previous, that get previous. All right. Absolutely. That's why we kind of trade space for time, right? That's kind of principle we spoke about. All right. If no further questions, let's now talk about nonlinear data structure. It's going to be a new lecture, okay? And okay. For your makeup lecture, I'll reach out to you about the contents, but let's now start a tree because that's going to be needed for your assignment number 3. And just before that, I think for the rest of the semester, I mean for the coming 6 weeks, we'll be mostly talking about trees. And as I said earlier in the semester, we don't really cover graphs in this course. Graph will be covered in the follow-up course, 3101. But for this course, we're going to focus on tree. But there are many things you can talk about trees. Okay, we'll go gradually. Make sure you grasp all the idea. Very fundamental. Okay. Before that, let me first of all tell you kind of the roadmap about the trees that we're going to discuss in this coming weeks, okay, about the trees. Okay, we got trees over here. So today we'll start a topic called general trees. And I will explain what general really means, okay? And we're going to talk about binary trees. And sometimes we just abbreviate it as BT, okay, binary trees. And this is the current lecture 6A, but just say A, okay? And then the third one, we're going to talk about something called binary search tree. Which has the acronym BSTs. You can think about the binary search trees are binary trees, but with some special property that we have to understand, mathematical property. Okay. And then we got another one called, okay, that's about B, actually, itself. Okay, so this will be part B. Okay, and then part C is going to be about something called balanced binary search tree. So we're going to get number 4. It's called balanced binary search tree. Binary search trees. And number 5, we're going to talk about something called priority queues, which is a very common abstract data type. But in your makeup lecture, I will talk about abstract data types, which has very simple definition. Okay. And then the very common data structure for priority queue is something called heap. And once we talk about heap, we're going to talk about heap sort. All right, so all these will be part C. All right, but we're going to go gradually one by one. But somehow we're going to follow this order here. Right? And of course, you can also use this as like a checklist where you study for the final exam. You can really want to ask yourself, what do I really mean by binary? What do I really mean by search? What do I really mean by balanced? What I really mean by like a heap. There's some heap property as well. Right? Yeah?
So for the balanced BST, are we going to learn the algorithm to kind of resort?
Yeah, so what Nathan was saying is there are certain kinds of balanced binary search tree where you can kind of restore the balance by doing some rotation. For example, like an AVL tree. That one there, I do have some pre-recorded lecture from the previous year, but I'm not too sure if I may have time to cover that in the lecture. In case I don't, I can include it as optional study for you guys. Not going to be covered in the official exam, but for those of you who might be interested, you can also go ahead. Yeah, we'll see. All right, let's now follow this kind of roadmap, and then let's now talk about trees. For today, it's still going to be a little bit light. I just want to introduce some terminology about the trees. And then not Thursday, for sure, you guys got something very important. And then after the makeup lecture next Tuesday, I will continue with some mathematical property for the trees. All right, let's now just talk about some general concept for the tree. Let's now look at the slides here. So we're going to understand, first of all, linear versus nonlinear, right? So this will be the first nonlinear data structure we're going to see. I'm going to put all the structure we have studied so far and put the tree into place and see how they differ visually. And we'll talk about terminology, general trees versus binary tree, and also how you can implement the trees in Java. So that will be the subject for your programming test number 2. So for your programming test number 2, as I said, we're going to put recursion, singly linked lists, and also trees all together. The best practice will be do your assignment number 3 and 4. Okay. Let's now see. We might get to some Java classes today, something light, but we'll get more. Okay. And then mathematical property for binary trees, and also something called tree traversal, which has to be defined recursively. So once you kind of understand the idea about traversal, all the kinds of algorithm you want to implement on the trees will follow more or less the tree traversal, which I'm going to talk about. I think a tree traversal hopefully next Tuesday, right? Still before the release of your assignment. If not, Thursday the latest. Okay, general trees. All right, first of all, let's now review what a linear data structure is. It basically has the concept about unique predecessor and unique successor. Somehow in the slide, I didn't really mention unique, but unique is really important, which I'm going to put on the notes. All right. Let's now do some visual recall about what we had earlier, right? So you can see here is our array. Here is our singly linked list. Here is our doubly linked list, right? So these are the three linear structure we have seen so far. Let's recall why they are linear, first of all, right? So we got arrays over here. We got our singly linked list, and we got our doubly linked list, right? So the idea is you should really have the unique predecessor and also unique successor. Okay, that's the idea. Let's say in the case of a singly linked list, that might be the most straightforward. If I am here, somewhere in the middle, in the list, if I want to go to the next node, there's only one reference that's available for me. So that's a unique successor. Unique successor. There's no way for me to go to another node that's also my successor. Unique. So unique here is really important. Okay. What about doubly linked list? In that case, well, you definitely got unique successor because you still got here, right? So that's only one link to go forward. You also got unique predecessor as well. The only way for this node to go to the previous one is follow the previous reference. So you got both unique successor and also unique predecessor, right? That's also justify why doubly linked list is also a linear structure. So also you got unique predecessor and successor. All right, what about array? Well, array is also very straightforward. For example, let's say if I am considering this middle element over here, the only way for me to go to, let's say this is index I to make it more general. How do I get to successor? Go to index I plus 1. That's the only way, right? So index I plus 1, also index minus I minus 1, right? So that would be the unique predecessor. That would be the unique successor. All right, so the notion about linear is actually very, very important, okay? Let's now talk about tree, which we're going to focus on for the rest of the course, mostly, okay? So when you talk about trees over here, to start with, at the top is something called a root, okay? And the way we talk about trees in engineering or in programming or computer science is kind of upside down. In real life, tree doesn't really grow upside down, right? It really grow bottom up. So that's something you gotta get used to, okay? So whenever we talk about the root of the tree, it's really at the top over here. And we said that the tree structure really got hierarchical data structure. Okay, I'm put it down here and I'll illustrate to you. So it really has the hierarchical structure. And one example you guys have learned earlier in 2030 is what you learned about inheritance. Remember we say one class can extend another class, right? As soon as you got so many extends keyword in your classes, you're basically building some inheritance relationship, which is hierarchical. For those of you who took a 2030 with me, maybe earlier, I'm pretty sure you've seen like a multi-layer, like a inheritance structure. But it's very straightforward. All right, hierarchical structure here. And then you basically got levels. So what I really mean by level is, you can think about this is what we call level 0. Okay? Level 0. So level 0, there's only one node. Let's say the root. Okay? And we got the next one here, obviously, level 1. And also we got level 2. And also we got level 3. There's a way to divide your nodes in this way, okay? And because this particular tree, you can see every node is branching out has 2 branches. Let's say this node here has 2 branches. Also, this node here has also 2 branches, right? At most 2 branches. It's a special case called binary tree, which we'll define more formally later. And in the case of binary tree, since you got levels so systematically, there is a way to really derive many nice mathematical properties according to the levels, which we'll do on Tuesday. The next Tuesday is going to be more mathematical than today. Okay, but I'll leave that for next Tuesday. So you got different levels over here, and then you can think about now when we talk about successors. If you got root over here, you got multiple successors in a way. I can either go to this node here, or I can go to this node here. Think about what's going to happen in the Java implementation. Okay, just imagine that, but you will see the code very soon. In the singly linked node, for example, we only got one single reference called the next, right? But now, in general, the tree may have as many nodes as possible in level 1. In that way, what will be the data structure to store? For example, it could be an array of nodes, or it can be a singly linked list of nodes, right? Conceptually. So this is something you will see in assignment number 3. So you can think about this one here. You got multiple successors of the root. And implementation-wise, we can store the next level nodes over here by using some linear data structure, which can be array, singly linked list, or doubly linked list, which can be stored in a linear data structure, right? Any of the 3 that we spoke about is possible. But for your assignments, we kind of choose the singly linked list for you. Okay? But in the example I talked about in the lecture, I gave you some example code about using array. So you get both. Okay. All right, so that's this page here. Just summarize about the difference between linear versus nonlinear. And then let's move on. Okay. Okay, good. No questions so far. Let's now move on. Okay. And when we talk about different terminology of tree, again, don't worry too much about ADT just yet, right? When you see the makeup lecture, you will see exactly what ADT really means, okay? So many terminology simply borrowed from family trees. So let's just see a few. We got something called the root, which I already showed to you, basically at the top. This unique root for each tree. And also we got parents, we got siblings, we got children. Also we got ancestor, we got descendants. Right? So these are some examples which you will see in a family tree in real life. But we're going to see how exactly they are defined in our context so that we can also program them recursively. All right? That's something we'll see. Let's now see terminology number 1. Okay? Let's go in this way. For each slide, let me just show you the terminology we're going to define, seeing some very simple definition, and I'll switch to talk about example. You really got to see example to really see what it is. Okay? Okay, this will be the tree I'm going to use throughout the today's lecture, but simple tree, right? That can illustrate many concepts, but I'm going to switch in a moment. But let's now, first of all, learn about root, and also learn about parents, and also learn about children. All right, so these are the 3 terms let's learn first, which is very straightforward. Okay, let's see here. So let's start from the root. So this, for the root, there's a unique root for each tree. So this is the unique root of the tree. All right? And this is the only node in the tree that does not have a parents, meaning that programmatically its parent will be null. The only node that has no parents. It sounds a little weird, but you know what I mean, right? The parents attribute will just be null. Okay, so that's about the root. And then parents and children are kind of symmetric. So for example, you can see for David right here, we say that the immediately following level, the nodes will be David will be the root's children. Okay, so we say that right here, Ernesto and Chris are the children of David. By the way, you might be asking, what about Elsa? We don't really consider Elsa as a child of David. We consider Elsa as descendants of David, which we'll get into. So whenever we talk about children, it's really the immediately below level of that particular node, right? Children. And the relationship is really symmetric. So Ernesto and Chris, because they are the children of David, of course their parents will be David, right? So you can think about programmatically, there might be some link called parents from Ernesto back to David. Okay, that will be the parents. Similarly, from Chris to David, there also is something called parents. So think about this part here is really bidirectional. That's basically what I'm trying to say. All right. All right, parents and children. We're done. And let's now talk about ancestor and descendants. Okay. Let me say one more thing. How about siblings? Siblings is also easy to say. So for sibling, it's really about the nodes that share the same parents. Sharing the same parent. Oh, just say, for example, you can see Shirley, Vanessa, and Peter right here. Because their common parents is Elsa. So we call them siblings. They're at the same level. Siblings. At the same level. And typically, the siblings, they will be stored in a linear data structure, as I said earlier, like in array, linked list, right? All right, let's now talk about ancestor and also descendants. Okay, that's a little bit more general concept than children. Okay, so what I will do is, let me keep this diagram clean. Let's now do another page. Okay, there we go. All right, right here. Let's now talk about ancestor and also descendants. I may have some definition there, but let's now take a look. Okay, there we go. What's really ancestor? So given a particular node, what would be its ancestor? Okay, guys, watch out. Ancestor over here includes n itself. That's our definition. All right, it's got to be n's parents, n's grandparents, all the way up to the root. That's the ancestor. All right, let's go over definition, and I'll show you an example. Descendants is going to be the other direction. Descendants, again, is going to include the node itself. So that means a node is both its ancestor and descendant at the same time. We kind of follow this definition. Okay, so the descendants will be n itself, n's children, and also n's grandchildren, and all the way down to the bottom level of the tree, right? Just the opposite direction. Let's see right away some example. Okay. Let's see, for example, let's talk about ancestor first. Okay. Let me choose maybe Sherry over here. Okay. So what will be the ancestor for Sherry? How many ancestor does Sherry have? 4? Okay, you guys are good. Not 3, right? Because Sherry herself should be her ancestor. Right? Okay, ancestor of Sherry. Okay, I think since they're okay, that's fine. So it's gonna be Sherry and also Elsa and also Chris and also David, right? 4 of them. And there's another very important concept called ancestor path. If I start with Sherry over here, so I start with Sherry. Okay, let me make it a bit thinner. I start with Sherry here. And then I want to follow the link of parents to go to Elsa. Once I get to Elsa, I want to follow the parent link to go to Chris. And then from Chris, I also try to follow the parent link to David. And for David, no more parents. Remember, the root actually has a parent now. So this is so-called the ancestor path for a particular node. Okay? So the way we actually write out the path is something like this. So we got Shirley, followed by Elsa, followed by Chris, followed by David. So this is the ancestor path of Sherry. And ancestor path is unique for each node because there's only a unique parents for each node. So that's why the path all the way to root will be unique. Okay, I'll write it down here as well. So ancestor path is unique. Unique because each node has unique parents. All right, that's good. Yeah, I'll just maybe annotate visually quickly. What about ancestor path for Anna? It'll be Anna, and then Chris, and then David, right? What about the ancestor path for David? Just David, okay? What about for Ernesto? Ernesto, and then David, right? Etc. Ancestor path, very, very simple. And let's talk about descendants. The simplest descendant you can have is like here, like the node at the bottom here, like a Sherry, Vanessa, and Peter. I'll say Vanessa, for example. So you might say the descendants of Vanessa will be just Vanessa herself. Even though Vanessa doesn't really have a children in this family tree, but herself is her descendants, all right? And which node has the most descendants? The root, right? Obviously, because you can see David here contains the descendants himself and every other node in the tree. It's going to be David, his children, his grandchildren, and also his grandchildren, all the nodes. Okay, I'll just make that annotation. So you can think about David is the root, has the most number of descendants. Basically, just all nodes. All right. Yeah, you can see more example on the slides. I think that's enough over here. Okay. And then let me just write one more thing here. This is on my notes. So you want to remember a node is also a node is both its ancestor and descendants. Right? That's a special property that we're defining. Okay? It's a definition we're following. Okay, not really property. All right, let's go back here. So we got ancestor, we got descendants, and then let's see, okay, what's the next? Siblings we already explained, right? Just basically node at the same level. Okay. And also, subtree. All right, this is important. Okay, subtree. Subtree basically is going to be the most important concept when you want to define recursive algorithm on your tree, right? To give an input tree. So let's now talk about it. So let's see the definition. When I say, okay, watch out here. Whenever you say a subtree, you have to say explicitly what's the root of that particular subtree. If you only tell me a subtree, I will ask you where is the root for that particular subtree. So if you say you're talking about subtree of a particular node being the root, then it's basically going to be the tree formed by all the descendants of n, including n itself. That's the definition. Okay. Let's now take a look over here. Okay, subtree. Let's talk about the smallest subtree. The smallest subtree apparently will be the node whose this number of descendants is just one, the node itself. Right? So why don't we say here, this will be a subtree. This is a subtree rooted at Peter. So you really want to make sure you specify who is the root of that particular subtree, right? So there's a subtree of size 1. Because there's only one node. All right, let's see another one. What about the subtree rooted at Elsa? Right, so that's another subtree here. Right, the root is Elsa. So this will be the subtree rooted at Elsa. Now the question is, what is the biggest subtree? Well, obviously the tree itself, basically, right? So the biggest subtree will be just the tree whose root is the absolute root for that particular tree. All right. And that one there, let's now just do that. So this will be the biggest subtree. Okay. So this is the largest subtree whose root is the absolute root of the tree. Okay, which is David right here. All right, so that's about the subtree. So we have seen 3 subtrees already. Okay. Okay, so far so good. And I want to just make another clean page to talk about another thing, because subtree is really important idea for you to really grasp, at least conceptually for today. And then as we go to more algorithm, you will also need to see that programmatically. Okay, let's talk more about subtree. If I talk about, let's say, this particular subtree, okay, what will be its size? Just 1, right? And, before that, subtree is really the units for you to call recursion on, really. Every time you're trying to maybe implement some recursive algorithm on the trees, you want to think, remember the general pattern we spoke about in the beginning of the semester. When, if they are not the base cases, the problem will be too big for you to solve. Let's say, for example, if I simply ask you to count the number of nodes in this particular tree, I'm giving you David, the absolute root. I'm going to tell you that the problem is too big for me to solve. What I can do instead is maybe I can recursively calculate what's the size of this particular subtree, and then recursively calculate what is the size of this particular subtree. Once I get a recursive return, add up these 2 values, so I will know what's the size of David plus 1, basically. Right? So that's a very quick conceptual sketch. I'll write it down. Okay. So several things you want to keep in mind. Okay. So subtrees are the subproblems for an algorithm to work. Oh, how about this? Let me say this. Let me be even more direct. For you to make recursive calls on. Of course, it depends on how many children you have, right? I mean, for the node. Okay. Let's say now the problem is, let's now consider one recursive problem. And we're not going to solve that in Java today, but let's see conceptually how you can understand it. So let's say we have a problem here. You might say, count the number of nodes in a tree rooted at n. Right? That's a problem. You're given some input, pretty much like for your assignment number 2, you're given some node which will point to the beginning of the chain of nodes, right? So now you're given a node which indicates which represents the root of the tree. Let me call this one here. Let's say count. Okay. Let's say the method we are defining is simply count. And then I say I want to start with count David. That's a problem I start with. Oh, sorry. So David, so here, so this here is really the only input we need over here, David. So this is the root of some subtree. Okay, so let's say that's how the beginning of our algorithm. We want to count how many nodes are there in the subtree rooted at David. Okay. Recursively, this is how you can think of. If I am given David right here, I want to know how many nodes are there, including David and all his descendants. It would be too difficult for me to solve right away. I'm going to solve that. I'm going to break it down into 3 pieces. Number 1, David himself will be counted as 1, right? Also, number 2, I'm going to recursively figure out what is going to be the size of the subtree rooted at the first child of David. And then I'm going to recursively figure out what is the size of the subtree rooted at the second child of David. All right, let's start with that. So you want to think about this will be David, which will be 1. And then you want to think about this will be something we got to count recursively. Recursively count the size of the subtree rooted at the first child of David. Right? That's something we're going to solve. And apparently, you can see Ernesto here is more like a base case because the node itself is already, right? It's basically already a root itself for that subtree. And then the third part is going to be the subtree that's rooted at the second child. Okay, let me also write it down. And then I'll show you how that's going to work visually. Okay, so for that one there, we got this particular subtree. Because there's only 2 children for David, so we only consider 2 subtree, right? If you got more children for that particular root, you need to deal with more subproblems, basically. Okay, so this will be also you gotta recursively count the size of the subtree rooted at the second child of David. All right, so far so good, right? So this already tells you how you're supposed to write your Java code because each subtree deserves a separate recursive call itself. I do have some exercise for you. And I'm going to show you some example code, either today or maybe Tuesday. Okay, but let's see exactly how it's going to work. Again, I'm going to have a clean page to illustrate to you. All right. And as I said, let's say we're going to start with David. We want to count. And then David. For which we don't know the answer just yet. In order to calculate it, we're going to count Ernesto. Right? It's more like a recursive call. And we're lucky, Ernesto here has no children. That's a base case. In that case, we can just return just 1. All right? Think about this more like a base case, which is going to return just 1. All right? Let's mark it down. Right? Just 1. And we can do the next one. We can try to return. We can also try to count quiz, which is going to count the size right here. Right? For that one, we don't know yet. Okay? And let's dive deeper. In order for me, so far, in order to count David, we're going to say 1 plus 1 plus whatever this result is. But we don't know what this is just yet, so we cannot know the result. Okay? What about count quiz right here? In order to count quiz, we have to count Elsa plus count Anna, and then plus 1. Agree? All right, let's now do that. So over there, we're going to say here, if I say count Anna, And I know that it's going to return 1 to me. It's a base case. And then I'm also going to count alpha right here. Okay, we're almost there. All right. So far we got the result for count Anna, which is already here, but we don't know what's count alpha just yet. It's too big. We're going to split it into subproblems. In order to count alpha, we need to basically say 1 here plus count Shirley, count Vanessa, and count Peter, right? Add them up together. Okay, let's do the final step. And we'll see how everything will be added up together. And then for this one here, we're going to say, I'm basically running out of color. So let's see here. Okay, that might be fine. So here we got count Shirley. And also we're going to count Vanessa. Okay. And also we're going to count Peter. Okay, each one of them is going to return 1, just themselves. So we're basically reaching the base cases for this particular subtree, right? We're reaching the base cases. We got count Shirley, count Vanessa, count Peter. Let's see what's going to happen, okay? So this one here is going to be 1. This one here is going to be 1. This one here is also going to be 1. What about count alpha? It's going to be 1 plus the recursive return. 1 plus 1 plus 1. Altogether, we got 1, 2, 3, 4, right? So that one there is going to give us 1 plus, okay, so I'll just say 4 here, but you know how the 4 comes from, right? Again, the 4 comes from Elsa herself and all the recursive return altogether. So that's 4. All right. And now we can count quiz because we got count Elsa being 4 plus 1 plus 1. That would be 6, right? So that one would be 6 right here. And then we know count Ernesto is 1, count is 6. 6 plus 1 plus 1. Count David should be 8. All right. Yeah, the number is actually right. Okay, I'm just checking. Right? So if you look at the number of nodes in the tree, it's actually 8. It is very important for you to understand this kind of recursive call visually, because the way things will work for every problem you're going to deal with is more or less following the same pattern. You somehow have to start with the root of the tree, and then you're going to split up the recursive call into different subtrees. And once you reach the base case, which will be at the bottom level, which we have some special names for them, which I'll get into. Once you get to the bottom node, so these are the special case, base cases which you got to return certain value, and then you got to aggregate all the values back up to the root. That's really one pattern you're going to see very often for recursive recursion on the tree. All right, but of course, we're going to see more later. Okay, if you don't mind, I got another question for you. Okay, let's now use another one here. Right here. Now, given this tree again, how many subtrees are there? How many subtrees in total? Hold on, Spence. Oh, you got a question? Okay, yeah, go ahead. Question.
Like about the definition of the subtree. Like,
Yes.
Should it contain all of a node's descendants? Would
Yes.
Shirley, Vanessa, and Elsa be a subtree of Elsa?
Mm-hmm. Okay. So whenever you talk about subtree, so just remember it's a subtree rooted at a particular node. So if you say if you talk about a subtree rooted at Shirley, it's only this subtree containing just one node. And then if you talk about a subtree rooted at Elsa, it's going to be all the nodes being the descendants of Elsa. If you talk about the subtree rooted at Chris, it's going to be all the descendants of Chris in that tree, right?
So you should include all of them.
All of them, all the descendants for that particular root. Question or you got answer?
Question. So following on, so if let's say we divided them further branches, so if we just took Chris and Anna, that wouldn't also then be a subtree. What would that classify as? If we just took Chris and Anna.
If you only got Chris and Anna, what do you mean? Sorry.
Okay, I'll clarify again. So the way, like, how she just said,
Uh-huh.
we take Chris
Yeah.
and then go into Elsa and her,
Yeah.
those kids, and then
Yeah.
Anna, that's all one subtree.
Mm-hmm.
If you just took Chris and Anna as a path, what would that be called then?
If you only take
Chris and Anna.
okay, only Chris and Anna. Okay, so normally when you say okay, when you talk about Chris, right?
Yeah.
One way to say that would be okay. First of all, how many children does Chris have? 2, right? And then there's another way to say how many subtrees does Chris contain? 2 subtrees. One subtree rooted at the first child, and the second subtree rooted at the second child. Right? So when you talk about, let's say, Chris and Anna specifically, maybe you're more talking about this parent here, and also the subtree rooted at the second child. Right? Thinking more about it, maybe we can clarify maybe a little bit later. Yeah?
Is it
12?
Yeah.
That's a very impressive number. I'm afraid not.
11?
Huh?
11?
Still not, sorry. I heard 8, yeah? 8, okay. Guys, how did you figure that out? There's a very simple way. Just count the number of nodes, exactly, because the very definition for subtree is it should have a particular node as a root. And how many possible nodes are there can be the root. All the nodes there, right? So this question here, if you see that in the written test, it should be a no-brainer. You basically just count the number of nodes in the tree, which would be 8, because every node can be the root of its own subtree. Okay, it will be A, which is the number of nodes in the tree. All right, but I'm going to suggest some simple exercise for you guys. All right, which I will suggest you try the table here, and then you're just going to say, okay, I'm here going to put the size of the subtree, and also you're going to talk about the size of this. Okay, I'll tell you exactly what I meant. So if I say 1 over here, I'm basically asking how many subtrees are there that's of size 1. How many? 1, 2, 3, 4. 4, right? Apparently, Shirley, Vanessa, Peter, and Anna. Those 4 nodes can be the root of that particular 1 node subtree. Okay, so we got 4. Oh, Ernesto as well. Beg your pardon, right? Should be 1, 2, 3, 4, 5. Exactly, yeah, 5. My mistake. Okay, 5. All right. And of course, you can try all the possible value. Of course, the maximum size of the subtree will be 8, right? In which case, there's only 1, which is the one rooted at David, right? Yeah, give a try to see if you got anything in between. Of course, it should add up to 8, right? We're still missing 2, if you see what I mean, right? Give it a try. That might be more likely what I might ask you during the test. I might say now each one to, what will be the number of subtrees that's either of size 5 or of size 2, in which case you got to figure out exactly, right? So that will require a little bit more analysis. All right. All right, so that's about the subtree, okay, which is very important. As we go for more recursive algorithm on the tree, I will always talk about subtree. And when we want to define mathematical properties on the binary tree, for example, later, we also need to define them recursively on the subtree. That's why it's so important. Yeah, Nathan.
What might be like the common use case of the size of a tree? Like when would we use is there a example where we might need it? Because it's kind of heavy to find if you don't store it.
I would say it's a little bit like a singly linked list, right? So remember, in the singly linked list, we can trade the space for time.
Yeah.
So if you don't really store the size attributes, in which case you have to go from the head all the way to when the current is null. So that's like a linear time in the tree as well. So if you didn't really store an attribute called size for the tree class, in that case, for you to figure out recursively, for example, it's going to be big over n because you got to count every node. So again, it's really hard to say which one might be more more desired. Is a balance, really. Whether you're okay to really take the cost of big O of n because you don't really need to access the size very often, right? So it really depends.
Yeah.
Yeah. Okay. Good question. Okay. All right, let's now move on a little bit, and then we'll take a short break, a little bit more. Okay. So now we're done with the subtree, and then, let's now talk about external nodes and also internal nodes. So these are also very simple concept. Okay. There we go. Okay. External nodes, the definition is simple. Let me see what I said in the slides. External nodes, simply the nodes without any children. All right. So you can see here, we got Shirley, and also we got Vanessa, also we got Peter, also Anna, also Ernesto. So all these nodes have no children. So these are so-called the external nodes. And you can already imagine how they can be useful when you want to define some recursive algorithm on the tree. So these will be the base cases. Once you reach some external node with without any children, you know that you're reaching the base case. All right. So these are so-called the external nodes. And sometimes we like to call them leaves of the tree. But most importantly, they are the base cases. All right. And then the rest of the tree, where you got at least one child, they are called internal nodes. So here, let's say we got David, apparently, and also we got Chris, also we got Elsa. So you can see each of these three nodes, they got at least one child. So here we got two children. So here we got also two children, and also this one we got three children, right? At least one. So these are the so-called external nodes. Sorry, internal. So these are the internal nodes. And then internal nodes, and then they are the recursive case, yeah. And only for those of you who might be in CS, it's now studying 2001, for example, right? Sometimes in the context of, like let's say a parse tree, which is another application for tree, right? I'll just mention that quickly, okay? So we call the internal nodes non-terminals. And we call the external nodes terminals. But if you're not studying that course, don't worry. Okay, just want to mention that. And by the way, compiler is actually all about trees. So you're basically going to extract your string text into a tree structure. So from there, you can do all kinds of recursive processing on the tree to generate something that's useful. Okay. All right, external nodes, internal nodes. Okay, let me see. Okay. So why don't we take a very short break, and then I only got a few more, but they are very important. We're going to talk about these concepts maybe right after the break. Okay? Why don't we take a short break by taking attendance, please? So there was a very good question during the break. Okay, I'll post it here just to share with everybody. We'll talk about subtree before the break. Is this a valid subtree here? No, but how do you justify that, right? Whenever you talk about a subtree, you must specify the root. So the root is Elsa here, apparently. But remember, it should really contain all the children and subchildren, etc. But Elsa's child also includes Peter, but it's not included. So it's not a subtree, right? A subtree rooted at Elsa? No, because Peter is not included. So you got to make sure whenever you talk about a subtree, you always want to think about what's the root. And that and the subtree should really contain all the descendants of that particular root. All right, just to clarify. Right, let's go over a little bit more definition, and then I just want to show you a little bit of Java code today, a little bit. At least you can see how the tree can be somehow constructed, right? Hopefully today, a little bit. All right, so let's now talk about, so we talk about edge, and also we talk about path. So these are, we already talked about ancestor path, right? It's pretty simple concept, right? So I just want to review that quickly, right? And then we'll talk about depth and also height. So edge is very easy. It's defined by a pair of nodes. For example, you can see here, between David and Ernesto, this is an edge. All right? So you can see here you got the child, you got the parents. So the pair, you can say, for example, David and also Ernesto. Okay, that's an edge, just a pair of nodes. And the idea about path, it would just be multiple edges connected together, right? For example, you might say here, this will be a path here, and a path, right? And of course, that's the ancestor path for NASA. So you can think about here, this will be the path. And we simply say Vanessa, Elsa, Chris, and David. And you can think about this is one edge, this is another edge, this is just another edge. So we got 3 edges in total in that path, right? 3 edges. And one thing you can kind of imagine, why would it be important to calculate the path, right? If you think about performance for tree, a little bit preview, right? If somehow my algorithm involves going from the root all the way to the end, I want to somehow know how long does it take me to really go from the root until the button here. In that case, well, I want to know what is the worst case. The worst case should really correspond to the longest path from the root down to some leaves. That should really correspond to the worst running time for my tree algorithm, right? That's just a look ahead. That's something we'll see as well. We'll be see a little bit more about like a bounce for the tree. All right, so that's about the edge and also path. Sorry, edge and path. Let's now talk about another 2, which are important. Let's talk about depth and also heights. Okay. So let me just make a new page over here. Right here. These 2 are closely related, so let's now talk about both of them together. But let's talk about depth first. Let's see the definition. Okay, for the depth, the number of edges from the root to that particular node. All right, so let's say, for example, the number of edges. Let's say what will be the depth for this particular node? The number of edges. 1, 2, and 3. We got 3 edges, right? In that way, so that will be the depth for this particular node. And you can, let's try to understand this visually first, and then we'll see how we can compute this programmatically once we see the Java classes. Let's see. So remember I talked about levels, right? You can somehow divide the levels of your tree by the depth of the nodes. So think about this one here is the level where the depth is simply just 0. Okay, by definition, it would be the depth of David. It will be the number of edges to go from the root, which is David itself, to David. There's no edges, right? So just 0. That's more like a base case, basically, right? The depth. And then what will be the depth for Ernesto and Quiz, right? It's going to be the number of edges from the root to this particular node. There's only one edge to go there, right? So this will be the level where the depth is simply 1. Okay, right here. So this will be the depth simply equal to 1. All right, and similarly, you can think about here. So for Elsa and Anna, because they're siblings, they will be basically a depth of 2. And finally, at the bottom here, we got a maximum depth, which will be, let me use a different color here. Okay, this will be the maximum depth that we have, which will be 3. So the depth is simply equal to 3. All right, let's understand this one first. Okay. Any question about depth over here? We're good? Okay. And then we now talk about something called the heights of the tree. And this one can be a little bit confusing, so I might need to use different copies of the pages to show you. Okay, but let me just clarify, first of all, in the definition. So whenever we talk about the depth of it's really of a node. You don't really say the depth of a tree. You don't say that. You say a depth of a particular node, because by its definition, the depth will be the number of edges from the root to that particular node. So you never say the depth of a tree, only a depth of a node. Number one. Okay, and okay, so let me just put it down. The number of edges or parent links. So for example, let's say Vanessa go to the parents, go to the parent, go to the parent. We got 1, 2, 3, 3 parent links, right? From the node to the root, right? And there's another term called the heights. Of a tree. How do we understand the height? Oh, first of all, the height, you don't really say the height of a node. You don't say that. You only say a height of a subtree, or maybe the height of a tree. Okay? Of course, in order to calculate the height of a tree, you need to know where the root is, right? But that's another story. Okay? Height of a tree. And what's the definition? You will see that also on the slides, it's defined as the maximum depth of its descendants. Yeah, I'm going to show you in a moment. Okay, but I want to emphasize over here. Whenever you say the height of a tree, you don't necessarily really mean the height of the overall tree. Of course, that could be one possibility. The David here is the absolute root of the tree. You can definitely ask about what's the height of this tree. That's one use case. But I can also ask, what is the height of this particular subtree? I can also ask you that. All right? That's something you want to be careful. So here, so that's why I say the tree here. You can also say it's a subtree, a little bit more general. All right, let's see different example here. So we already know about calculating the depth, and let's now see how we can calculate the heights of a subtree. Okay, I'm going to put 2 copies over here, so you will see side by side. Okay, right here. So let's say, number 1, I want to know what's the heights of the tree rooted at David. And the second one, let's say I want to know what is the heights of the tree rooted at, let's say, Elsa. Right? You can see here I'm talking about the root being David. And here I'm talking about the root being Elsa. Right? I'm really talking about different contexts over here, but it's going to be the same definition. Right? So let's not worry about calculating this recursively. Once we see a Java code, it'll be easier for me to discuss. But let's talk about conceptually. How do you see? Okay? Let's do the non-recursive way. We said earlier, with respect to this particular root, so we got depth being equal to 0. Over here, the depth is equal to 1. And here, the depth is equal to 2. And here, the depth is equal to 3. However, you don't really want to draw it like that every time, right? It's kind of time consuming. So I would suggest draw it this way. Okay? Why don't we just try to annotate each node with some number? So here, David, you can say depth is equal to 0. So here, I can say the depth is equal to 1. Depth is equal to 2. And the depth is equal to 3. And also here, sorry. Somehow it got disappeared. Okay. Okay, never mind. And the depth is equal to 3. Okay. Not too sure why I got it disappear, but I'll just put it back for now. Okay, good. Are you okay with the annotation, right? It's about the depth. And the d value here is relative to the root of David. On the other hand, what about this particular problem? Should we worry about David, Ernesto, and Chris? We don't worry about them because they are not part of the subtree. We only worry about Elsa and her descendants right here. So we should start with that. So what I would do is, in this case, I'm going to say d will be equal to 0. D will be equal to 1. D will be equal to 1. D will be equal to 1. This is the common confusion you might have, right? Whenever we talk about heights of a particular subtree, you really should define the d value for each node in that subtree accordingly, right? That's the most important thing, all right? And once we got this annotation written down, by definition, the heights of the subtree rooted at David will be the maximum depth of the children. Maximum depth is 3. That's it, right? The maximum d value, which will be just 3. And what about the heights of the tree rooted at Elsa? Maximum d value, which will be 1. All right. Are we okay with this? All right. So here I'm just showing you maybe the more intuitive way to see the depth and height. But when we calculate them, we're going to do them recursively, which we might get into maybe a little bit later. Okay. I got 4 minutes. I would suggest at least I show you a little bit of Java classes, right? And then we can see some more manipulation maybe next time. Okay. There is really some crazy line of Java code I may be nice to really show to you today. Okay. Yeah, I'll go to here directly. There are some clarification which I can do maybe on Tuesday. Let's just do this one here. Okay. So this will be the tree node class that you're going to more or less need for your assignments, except for the children, I just use an array. Okay. So let's see this. So you got tree node. That's the class. Again, it's generic, right? You guys should know about generic pretty well. You should really get prepared for Thursday, right? Tree node. And then what references do we have? We got parents and we got children, right? You can see we got a single tree nodes. And then we got an array of tree node as a children right here. Right? So as soon as we see the attributes over here, how do we visualize it? Let's do that right away. Okay. Oh, by the way, we also got something called elements. After all, the reason that we want to create a different data structure is for storing elements like a data, right? Don't forget, we should have that as well. So the way to visualize is like this. So in the runtime, we're going to have some objects of type tree nodes. And of course, the E here can be instantiated to any type. Can be a string, can be integer, can be person, right? Let me just say string, just for now, all right? And then we got 3 main attributes here. We got elements. For example, element can be maybe, let's say, Alan, right? It can be storing Alan. And also we got parents. And also we got children. I'll say C here. Let's say if Alan happened to be the root, so the parents can just be none. Otherwise, it might be pointing to another tree node, right? It's parents. What about children here? Let's visualize that quickly. The children here is going to be an array of tree nodes. And the way to visualize it will be that one is going to point to the beginning of an array, and then it's going to be of certain size, and then each one of them is going to be the root of a subtree. All right? So for example, let's say for this one here, for element 0 is going to be a tree node. So it could be that it's going to point to a tree node right here, and then that one there has maybe elements, parents, and also children. The element maybe, let's say, Mark. And the parent is going to be symmetric. it should be pointing back to this particular tree node because Alan has a child, Mark. Mark should have the parent, Alan, symmetrically, right? And also here, the children over here will just be another array of the grandchildren of Alan, basically, right? So this will be more or less how the runtime structure will look like. The only difference is for your assignment number 3 and 4, the children structure here is not going to be an array. It's going to be a singly linked list. That's what you will see. Okay? Good. Guys, I think I'll leave this part here to give me 30 seconds. I'll leave this line here for Tuesday for discussion. I want you guys to really look at this line here, right? This is a Java workaround for creating generic array. Okay, take a look at that to see if you can make some sense out of it. It's a really crazy line to write, but you need to know how to write it. Okay, take a look, and then maybe for next Tuesday when we come back, and then I'll explain that. All right, thank you so much, and then I might see you either Wednesday or Thursday during the test.